Okay, Cashify. So I thought a little bit more about this, and we were talking about time and time dilation, and so I neglected to mention or take into account. Well, I took it into account just in my previous thinking, but anyway, I didn't mention the dilation or contraction of space as well, distances. So, for example, let's say we have two planets that are not at relativistic speeds with respect to each other, and they're 10 light years apart, and I'm going to travel on a spaceship from planet 1 to planet 2. Well, when I take off and get to this near light speed, that distance of 10 light years, depending on my speed, let's just say I have exactly the right speed, going over 9/10 the speed of light relative to these planets, that distance could contract to 5 light years. But a couple things I want to note. First of all, as we go faster and faster, and again, I caution you against making assumptions or drawing conclusions about what's happening at the speed of light. General relativity says you can't get to the speed of light. So while we're approaching time stopping, that doesn't mean you can actually jump to that asymptote and use the equation. It's kind of like dividing by zero. You can have a limit of 5 over n as n approaches infinity, as n approaches 0, and the limit is infinity. But that doesn't mean you can divide 5 by 0 and say the answer is infinity. But anyway, we're accepting those assumptions because they're a little bit of a clue, and it's definitely a fun thought experiment. So anyway, there's a couple things I want you to think about. One, as the time slows down on the spaceship, that's what we see on planet 1. Looking in a telescope at that spaceship, we see those people moving slowly, and time is slowing for them. Their clocks are ticking, their distances are dilated. But on the ship, so we see their ship, for example, is shorter. But on the ship, it seems just as big as it always has. Time is flowing at the same rate it always has. And we see on the ship the people and the clocks on the planets have slowed down. So if you want to apply this general relativity idea to light speed travel and say time stops, you have to keep in mind that there is no such progression on how time seems to you on the ship. So when the ship does finally achieve light speed, we have every reason to think that time still appears to flow for people on the ship. It's everything outside the ship that we're going light speed with respect to that will have frozen in time. So that's rather odd. Now, I think for complex human systems that's pretty difficult, because if we are moving baryonic matter at near the speed of light, this makes sense because it's near the speed of light with relative to these planets. Relative to another planet, I might be going half the speed of light, and another planet maybe it's traveling along with me and I'm at rest with respect to it. Photons are different. They go the speed of light relative to everything. Okay. Now, I think as a human being, it's difficult because we're talking about using telescopes to look at these things. Well, a photon in free flight doesn't have any of those opportunities. A photon in free flight is in a quantum isolation until it interacts with some other system, some other particle. It's in this quantum isolation. So there would be weird quantum effects too, that the rest of the universe not only has time stopped, but it is in every possible state that it can be simultaneously. Okay, so how could this be? Well, it can't exchange any information with that outside world. So it's not so much what the outside world has become, but the fact that no facts can really be stated about that outside world, because there's every contradictory synthetic fact possible would apply, and so really this is a part of the universe that's not interacting with that photon during that period. So while the photon is in this weird relativistic state, the rest of the universe sort of becomes irrelevant. Yeah, space loses relevance, time loses relevance. Okay, and then the final thing I'd like to say, though, is it's important for people to realize that light does not always travel at the speed of light. When light goes into, for example, a big block of glass, or through any glass, all glass is big relative to light, but just imagine it in a big block of glass. It's actually traveling slower than the speed of light. Inversely proportional, I think. I should have checked this. I got the internet. to the refractive index. Anyway, the refractive index is a factor in that. I believe it's inversely proportional. But whatever, the speed of light slows down in a material, in a medium. Well, the vacuum of space is not really a vacuum. There actually are particles out there, and theoretically, there's a theoretical proposal that there's this Higgs field that permeates all space, that really is space, and the phenomena of space has to do with the way Higgs bosons interact. In which case, there again is a medium of particles out there that the light is traveling through. But even forgetting that, there is diffuse, hydrogen and stuff in space. So that is a material. And so the refractive index would be, very, very low, but there still would be one. So it could be that even in the near vacuum of space, that light doesn't actually achieve the speed of light. So that's interesting to think of. Now, this last thing I don't necessarily spend a lot of time thinking about, just because, I think that I think there are other explanations for why light travels. And since, light traveling through space is like a superconductivity phenomenon, at least on this Higgs field kind of theory, that its photons are able to travel in a superconductive kind of way, I think that answers why it probably is traveling at the speed of light. Okay, so just like the resistance in a conductor gets lower and lower when you cool a conductor, and in superconductors it actually reaches zero before the temperature reaches zero. Well, I think there might be a way to reach light speed before actually getting a refractive index of zero. But it's worth thinking about, because if you're going to draw conclusions from science, I endorse that. That's what I've tried to do. But you have to be kind of careful, And so the first thing to be careful about is thinking that time actually stops, when in reality general relativity doesn't say that. Think about that limit of 5 over n as n approaches 0, and how that relates to assumptions you might make, how that metaphorically applies to this issue of whether time actually stops, whether we can say that, just because the limit of this, the limit of the slow time distortion is 0 at infinity. And then also just the small things like that maybe light is traveling even a little bit slower than light. That's just the unknown elements, and take them into account. And then not really. I think you shouldn't really be so. You're proactive in asserting this the way you would like to see this stuff. You say that everything happens at once for the photon. Well, no, the photon's life, the lifetime of the photon between when it was emitted and absorbed, that might all happen at once in some sense, for who knows what reference frame. But really, if that light, if we're taking general relativity as if I'm on a spaceship, the photon is a spaceship and it's traveling at the speed of light, time stops for everybody else. So the moment that photon's created, everything else gets frozen. Okay? And the moment it's absorbed, everything starts going again. Now, the odd thing is that we know that light does have a finite speed, and that things do change while light is in motion. So that's an odd paradox, but it has to be sorted out. You can't just ignore the contradictions and take the side of the contradiction that you want. Take the implication that time stops and forget about the fact that no, in other reference frames time hasn't stopped, and you need to maybe up your relativity to the point where you can understand that, yeah, this is the point. I'm on a spaceship traveling between two planets, and on the planets it seems that time is, for me, looking at the planets, it looks like time is slowed down on the planets. For the people on the planets looking at me, it looks like my time is slowed down. How can that be? How can we both see the other is slowed down? And the answer in general relativity has to do with the fact that the spaceship starts in a planetary reference frame and eventually decelerates and re-enters the planetary reference frame. And so it's the planetary reference frame that will win in the end when you correlate these frames back together by bringing the rest frames together. And if you never did that, it would never get correlated. And that's rather odd, because each of us would see the other as going slower forever.